Hello and welcome to this tutorial. Now let's solve this challenge question on the board. And I read, assume you are agile enough to run across a horizontal surface at 8.50 meters per second, independently of the value of the gravitational field. The first task is what will be the radius, okay? Then the second task is what will be the mass of an LS spherical asteroid of uniform density 1.10 times 10 to the power 3 kilogram per cubic meters on you could launch yourself into orbit by running. That means to launch oneself into orbit, by running on an asteroid. Of course, the runner speed must be equal to the orbital velocity. Yes, I said orbital velocity because this is not the case of escape velocity. It is escape velocity when we talk about the minimum velocity required for an object, to escape from the gravitational pull of a celestial body. That's in the case of escape velocity. And the body will now travel into interplanetary space. That's in the case of escape velocity. But when it comes to orbital velocity, that is the minimum velocity required for an object, okay, to stay or to maintain or to continuously orbit a celestial body. That's in the case of orbital velocity. And it is orbital velocity because it will allow an object, to continuously orbit a celestial body, okay, and it will not move towards it, okay, or break away from it, unlike the case of escape velocity. Okay, it allows an object to break free from the gravitational pull or the gravitational pull of a celestial body, okay, and the object will escape into space, and that's it. All right, so in this case, and the last question is what will be the period. So let's look at this one after the other, just like I explained. When it comes to orbital velocity and escape velocity, it is orbital velocity. Okay, first we want to calculate radius. Okay, so it is orbital velocity. Orbital velocity is when we talk about parking orbit, when the centripetal force, that is a circular force, or yes, this is the force that keeps an object moving or to keep an object in an orbit is equal to the gravitational force on the object. So that is like if you have centripetal force to be equals to gravitational force, this will be mv squared over r, which is centripetal force. This will be gravitational constant multiplied by big M, then small m over r squared. When we divide both sides by r, okay, when we divide the denominators by r and also divide the numerators by m, okay, we're going to have this reduced to v squared equals to gm over r. So this is what we call orbital velocity, which will be square root of g capital M over what? Over r. So we have the formula for orbital velocity to be square root of g capital M over what? Over r. Now, when we look at the question, we want to calculate radius, okay? So let's not forget that g represents universal or gravitational constants. Gravitational constants, okay? And the value of g is 6.67 times 10 raised to the power of minus 11 Newton meter squared per kilogram squared. That is the universal constant. Now, m is the mass of asteroid. According to this question, the mass of asteroid is m, but we are not giving m. But let's not forget that here we are giving that the mass of an LS spherical asteroid of uniform density 1.10 times 10 to the power of 3 kilogram per cubic meters on you could launch yourself into orbit. So that means that because we know that density is mass over volume, okay, so we can say that mass is density times volume. Okay, now volume of asteroid will be same as volume of a sphere, and that's it. So which means mass equation will be density multiplied by 4 over 3 pi r cubed. Okay, So we then substitute for m in this case. But first, let's express r in terms of gm. So r in this case will be equals to gm over v naught squared. That's it. So by the time we now substitute this for m, we're going to write r equals to g multiplied by density multiplied by 4 over 3 pi r cubed divided by v naught. This divided on both sides. This we leave this the left hand side to be what? 1. So we have 1 equals to g multiplied by density times 4 over pi r squared over v naught. Now let's not forget that we want to express r in terms of orders. Okay, so in this case the radius will be square root of, it's going to be square root of, let's not forget that this will be squared. This is having a square, so it will be the square root of, so if you have square root of v squared, that will be v naught square root of v naught times square root of 3 over, that's 3 over 4 pi g density, 4 pi g density. Okay, yes, 4 pi g density, and that's it. All right, so this is the formula for the radius. Now, what is v naught? V naught, which is the orbital velocity. The orbital velocity is 8.50 meters per second. And we have here that the gravitational constant, which is universal constant, is 6.67 times 10 raised to the power of minus 11. Then we're also given the density of asteroid. So density of asteroid, density is 1.10 times 10 to the power of 3 kilogram per cubic meters. That's the density of asteroid. What else? You already know what this is. Okay, so we just plug in the values. Okay, we plug in the values. Okay, this is 1. Yeah, so that's it. So we can then have radius to be equals to 8.50 times square root of 3 over 4 multiplied by 3.142, which is the value of pi, multiplied by universal constant, which is 6.67 times 10 raised to the power of minus 11, then multiply by density, which is 1.10, okay, multiply by 10 raised to the power of 3, 10 raised to the power of 3. Okay, so let's just multiply and do others. Okay, so we have what is 4 times 3.142 multiplied by 6.67, okay, then multiply by 1.10. Okay, so then r will be 8.50 square root of 3 divided by, this will be 92.211416. Okay, now this, when we combine the powers of 10, this will be 10 raised to the power of minus 8, so which will be r equals to 8.50 square root of 3 times 10 raised to the power of 8 over 92.211416. Okay, so what is 3 divided by 92.211416? Okay, so this will be r equals to 8.50 multiplied by, this will be 0.0325253. Now 10 raised to the power of 8, that will be 10 raised to the power of 4. Square root of 10 raised to the power of 8 is 10 raised to the power of 4. Okay, so let's get the square root of 0.03253. So that will be r equals to 8.50 multiplied by this value, which is 0.1804 approximately times 10 raised to the power of 4. So when multiplied by 8.50, okay, so r will be 1.5331. times 10 to the power of 4. Okay, so that will be 15331 meters. So this is the radius. That's the radius. Now the second question is to calculate the mass. So mass of LS spherical asteroid. Mass of asteroid. So the mass of the asteroid, we got that from here to be mass is density multiplied by 4/3 pi r cubed. So the density, this would be mass of asteroid will be 1.10, which is density times 10 raised to the power of 3. Now 4 divided by 3 is the same as 1.33. Yeah, 4 divided by 3, yeah, that will be 1.33. So this will be 1.33 multiplied by 3.142. Then we calculated the radius to be 15331, then cubed. So let's just multiply all of that. Then multiply by 3.142, then multiply by 15331 to the power 4. So that will be 2.54546 times 10 raised to the power of, for that only we got times 10 raised to the power of 17, then multiply by 10 raised to the power of 3. So the mass will be equals to 2.546 times 10 raised to the power of 20. That is the mass, times 10 raised to the power of 20 kilograms. That's the mass. Okay, so the last question is what will be the period? Okay, so what will be the period? That's C. Now let's calculate period. Now the period in this case will be 2 pi r over the orbital velocity. So we got r to be this. So period will be 2 multiplied by 3.142 times. So we have t to be equals to 2 times 3.142 multiplied by the radius, which is 15331. Then we divide it by 8.50. So now this will be t equals to 3.142 multiplied by 2, then multiply by 15331. That alone is 96,340.004. Then that will be divided by 8.5. Divided by 8.5. Okay, so that will be t equals to 11334 approximately seconds. And that is the time period, the mass, and also the what? And also the radius. The noblest pleasure is the joy of understanding. Bye-bye.